Retaining privileged information for multitask learning. In classic supervised learning, one tries to find a hypothesis model that maps from the example features to the label space. There is often a trade-off between the expressiveness of the hypothesis model and sample complexity required to train it. So on a typical dataset, what we often find is that the targets are not distributed uniformly in terms of the sample size. So for perhaps a large number of tasks, we may not have enough samples to train an expressive model. So this motivates the use of what's called the privileged information, otherwise known as PI. And one can think of PI as a set of auxiliary features that can describe the targets really well, but they're only available during training time and not test time. So naturally, we want to know how do we incorporate the PI into the training process effectively. Naturally, one way to do this is to use them as auxiliary targets during training. But one of the problems of doing this is that it's hard to know beforehand when you have multiple tasks whether the PI will contribute positively or negatively towards the learning of these new tasks. Alternatively, one can use a data fusion scheme in which one tries to learn a fused representation of the example features in the PI. However, one problem with this is that if the hypothesis model over-relies on the PI during training, it could lead to poor generalization during testing when the PI is unavailable as an input. Another learning scheme is called learning under privileged information, otherwise known as loopy. And under this setting, one tries to learn a teacher model that maps from the PI to the label space. It has been shown that by aligning the feature spaces and the hypothesis spaces, this loopy setting can dramatically decrease the sample complexity required to train your original model. So our goal then is, given a set of PI for a particular task, can we decrease the sample complexity of related tasks in a multitask setting? So in our proposed method, we first decompose the privileged information into a set of vocabulary words. Our goal then is to learn a vectorized representation for each of the words in the PI dictionary. So during training, when we are given a set of example features, we treat the PI as a source of label information that informs what distribution over the PI words you should output to adequately describe your set of example features. And we call this the matching function because at test time, when the PI is unavailable, we can still use the matching function to output a distribution over the words that can describe the test set example. And we simply sum over the distribution over the PI words to obtain this augmented representation of the example features that contains the PI information. And we can further train this matching function by maximizing the distance between positive and negative samples in this joint feature space. Once we're given multiple tasks, we can partition the training sets into two general pools, a pool for the positive samples for each class and a pool for negative samples for each class. We then deploy this multitask sampling scheme in which we sample a fixed number of positive samples and a fixed number of negative samples for each class. And now the matching function has information from across multiple tasks that can inform how it should partition the augmented representations in the joint feature space. So in our paper, you'll read about evaluations of our method against other transfer learning methods for incorporating PI. We also provide an analysis of the sample complexity of our method, as well as show how our method can be used to solve the long tail problem of VHRs. Thank you, and we hope to see you at our presentation.